Assalamu alaikum. Welcome to the lectures of linear algebra. Today we'll talk about eigenvectors and eigenvalues. Um, now, before we go into the details of these topics, I hope that you have understood what we have talked about, difference equations and Markov chains. Because if you have understood those, these topics will become very easy for you to understand. Now, I think of a matrix A, be a transformation matrix, or and then there's a set of vectors u and v. So a vector, if you look at this vector u, then you can think of existing in the second quadrant of a two-coordinate system, in which it will be a negative -1 here and a +1 here, and now you can think of v as 2 here and 1 here, right? So if I multiply a with u, the resultant vector will come out as -5 and -1. It means this u vector has now transformed to this vector, and similarly this vector has transformed to this vector, right? Now in the previous lectures we talked about the steady state vectors, in which we said that a times or p times, whichever what you want to say, that a times q is equals to q. These were called, q was called the steady state vector. It means if you multiply with the transformation, this transformation will not have any effect on q, right? And of course a was, in that scenario, was a probability transition matrix, or you can say it's a steady, you can say the stochastic matrix, right? Now in this section, in this scenario, we are actually looking at finding the solutions for these kind of transformation, in which you have aq is equals to q. Generally, you can generalize the scenario in a sense that this translation, say for example aq times q is a translation that basically results in q, or you can think of a translation of vector v by av. You can, so v was 2 1 and av is 4 2. It means they are existing on the same line, right? So in general, so if you look at a generalization of the scenario, you can think of finding the vectors that when I multiply a transformation matrix with it, right, they first of all, they will not change, and even if they change, they actually linearly scales on that line. So it means I can think of ax being multiplied and getting an answer of 2x. So it means if x was here, right, and multiply with ax, it necessarily becomes 2x, right? So that transformation remain on the line, right? So what you can do here is any transformation that actually becomes nothing but a linear scaling of that vector. Okay, so these kind of vectors, or these kind of solutions, right? Say for example in this case ax equals 2x, right, is actually what we call is the eigenvalue of that matrix, right? And and the resultant vector is actually, in this case, vector x is an eigenvector, because this vector just scales linearly. If you mean multiplied with the transition matrix A, it will just scale linearly by the value with certain dates, say 2x, right? You can think of a scenario as -4x, right? So what kind of values are possible for which this linear scaling actually exists? This is called eigenvalues, and the vectors for which that exists is called eigenvectors. So we can define an eigenvector as an eigenvector of an n cross n matrix, right? A, and is a actually this x is a non-zero vector, is a non-zero vector x such that you have ax is equals to lambda x. So the vector x, when multiplied with the straight transition matrix A, what happens is it's just linearly scaled by the value lambda. This is called the eigenvalue, this is called the eigenvector. Okay. Now a scalar value of this lambda, right, is must have a non-trivial solution of x, right? And the corresponding x is called the eigenvalue, eigenvector corresponding to lambda, right? This is eigenvalue, and the corresponding vector respect to this eigenvalue is eigenvector. Okay. Say for example, now again that matrix which we discussed earlier is now 1, 5, 6 and 2, right? And u is nothing but 6 and minus 5, and v is equals to 3 and minus 2. So we've been asked, are the vector u and v are eigenvectors, right? So if they are eigenvectors, right, so it means a times u, remember a times x, it should be lambda times u, right? Okay. So in this case, I will multiply with a with u, right, so which is 1, 5, 6 and 2 multiplied with 6 and minus 5, it must be some linear scaling of the vector u. So if I multiply that, it becomes 6 minus 30 becomes minus 24, and this becomes 30 minus 10 becomes 20, right? Now if I take 4 common out from here, minus 4 actually, so that comes 6 minus 5, 6 minus 5, and this comes out to be minus 4. So this is again the vector u, or should write the other way around, but anyways, this becomes lambda times u, right? So u is the same here, lambda is minus 4. So it means you can write this in terms of the eigen representation, which is au times equals to lambda times u. Now we can do the same calculation for av, right? So when you multiply with av, it becomes 1562, and when you multiply with v, which is 3 minus 2, this comes out to be minus 9 and 11, right? And there is no way I can represent this minus 9 and 11 in terms of as a scaling of 3 and minus 2. So it means this is not equals to, it is equals to, but this is not equals to lambda times v. So it means this is v is not an eigenvector, and of course there is no such value of lambda exist over which v can become an eigenvector, right? Now say we can actually find the eigen vector corresponding to A. So if A is that matrix which is 1, 5, 6 and 2, we've been asked to find the eigenvector x, right? So what you do is simply is ax times lambda times x, right? Now it means ax minus lambda times x is equal to 0, and you can write this a minus lambda, actually I lambda x equal to 0. So again this is equal to finding nothing but a homogeneous system linear equation, and you can find this nothing but as say which is 1 minus lambda, 6, 5 and 2 minus lambda. luckily in that example we've been told we have to verify, we've been told that lambda is equals to 7, right? Lambda is equals to 7, though you can actually find it from that lambda is 7 is the eigenvalue, but we will see that in probably the next lecture, that how you can find the value of lambda here. But luckily here somebody told us that lambda value of lambda is 7, so in this case this matrix will become minus 6, 6, 5 and minus 5, right? And again this has to be a minus I times lambda. So what you have to do is to augment this matrix and simply find the solution of this homogeneous equation, which is minus 6, 6, 5 and minus 5. And if you do a simple bit of calculations and augment it with 0 and 0, you will actually end up with 1, minus 1, 0, 0 and 0, right? So again we have got a free variable here, which is in this case x1 minus x2 equals to 0 and x1 is equals to x2, so x2 is a free variable. You can write the solution for this one as x2 and x2, which is 1, 1, x2. So again the solution here is 1, 1, x2. So the solution to this homogeneous equation is 1, 1 times x2. So if you choose any value of x2, there will be an eigenvector. So if you say x2 is equals to 1, so this is an eigenvector. If I say x2 is equals to 2, then you have 2, 2 as eigenvector, and so on. You have an unlimited possibilities of eigenvectors. So it means any vector that you choose, any multiple of any value of x2 that you will choose, you will have the eigenvector. Okay. Now generally eigenvector must be non-zero. Eigenvector generally is non-zero by definition, but eigen value may be non-zero. Okay. Now in that case there is a case in which the number 0 is an eigenvalue, and we will discuss it later, hopefully, in this lecture. Okay. Now, so what we have done is carried out the row reduction to actually find out the eigenvectors, but this cannot be actually used to find out the eigenvalues, right? It is not recommended to use an echelon form of matrix to find out the eigenvalue of that matrix. Okay? Now in this case, you can think of this as ax is equal to lambda x, and we wrote that as a minus lambda I times x is equals to 0, and it has if and only if it has a non-trivial solution, right? From discussion of it has a non-trivial solution. So it must have a non-trivial solution, because if it has a trivial solution, it means the value of x will become 1, the value of x will become 0, and we know that eigenvalues may be 0, but eigenvector must be non-zero. So it means lambda can be 0, but x has to be non-zero. It can be 0 in certain cases, which we will see in let's say in 10-15 minutes. Okay. Now so it means we know that from our basic vector space theory that this matrix, which is a minus lambda I, will actually form a space, and this subspace is actually called an eigenspace. Eigenspace of A corresponding to lambda, because for every value of lambda, different value of lambda, you will have a new eigenspace, and this is actually, to be very specific, it's nothing but the null space of that matrix, as we already know, right? Now so in the previous example, like the one we did here, in which the value of lambda is equals to 7, you can think of eigenspace as something like that for lambda is equals to 7, which will be a line through in this point here. Let's say this is 1 1. This was the vector that we found out, 1 1 x2. So this was x1, this is x2, so this is 1 and this is 1, so and the eigenvalue was 7, so it means this vector when multiplied by 7 will go to at 7 here. So this is your line here. You can think of this as a line here passing through that. Okay. So this actually multiplication, which by a this vector a by this matrix A will actually shift it to this point here. Similarly, there also lambda is equals to -4 is also an eigenvalue of that matrix, which means Ax is -4 times x was also the eigenvalue here. So in this case, the matrix was solution was actually -1 and 2, as we found out in the previous example, and then it's a line here again, and again this is the eigenspace. This is eigenspace for lambda is equals to -4, and this is the eigenspace for lambda is equals to 7. Okay, and again so actually you can find out the eigenspaces, and each value of lambda, as you can see, will generate actually a different eigenspace. Okay, now say again we can be asked to find the basis for that eigenspace, and say if our matrix is A is equals to 4 2 2 -1 1 -1 6 6 and 8, and we've been given one of the eigenvalues, which is 2. We have to find the basis corresponding to this lambda, right, which is 2, right? To find a basis for the corresponding eigenspace. Okay, now in that case we know that it will become A minus 2 times you have A minus 2 times I, actually should be a hereditary matrix here, and x should be equal to 0. So A minus 2i, again solution to the homogeneous system linear equations. A minus 2i will become as nothing but 4 minus 1 6 2 1 and 6 2 minus 1 8, and that will be minus 2 times 0 0 0 2 0 0 0 2, and that comes out to be 2 2 2 minus 1 plus 1, and again minus 1 6 6 and 6. Now we can again apply this augmentation to solve this problem. Minus 1 1 minus 1 6 6 and 6, and augment with 0 0 0. So again, if you subtract the first row from the third row, then you can actually reduce that, and similarly you can subtract it to row 2 and further reduce that. The answer comes out to be 6 0 0 0 0 0 0 and again 0 0 0. So we can see here that we have two free variables, and and in this case you have 2x1 minus x2 plus 6x3 equals to 0, and I can find the basis for this thing here, which is x1, x2 and x3, and which is x1 is nothing but I can write this equation in purely in terms of x1, which is minus 1 by 2 times x2 plus 3x3 minus 1 by 2 times x2 plus 3x3. This is x2 again, this is x3 here, right? Again I can separate that out, which is nothing but minus 1 by 2 1 0 x2 plus 3 0 1 times 3. So again, sorry, minus 3 here, so that were minus coming out and they have to be plus here, sorry. And then of course it means these are two vectors, and you know that this is nothing but because x2 and x3 are the free variables, they form a subspace, right? And this subspace has these two vectors as the basis vectors, right? So you can think of this as scalar coefficients, and this as vectors which are spanning the whole solution set of this homogeneous system of linear equations. So we have this basis as 1 2 0 and minus 3 0 and 1. And again, if I in this case, now we can see that eigenspace will not be a line, it will be a plane, right? So in this case you can think of the plane scaling, kind of scaling on a plane. So one of the main properties of the eigenvalues are that eigenvalues of the triangular matrix, a very shortcut to find the eigenvalues. So one of them is if the eigenvalues of a triangular matrix are the entries on its main diagonal, So if there is a triangular matrix, either upper triangular or a lower triangular, let's say in this case, let's say A is equals to A11, A12 upper triangular matrix, 0, A22, 0, 0, A33, right? So if we subtract this by A minus lambda I, so I can write this as subtract by lambda, which is lambda 0 0 0 lambda 0 0 0 lambda, and this comes out to be A minus lambda I as A11 minus lambda A12 A13 and 0 A22 minus lambda A23 and 0 and 0, and this is A33 minus lambda, right? So this equation has a solution. We will have a lambda as a solution or the eigenvalue of A if and only if equation we know that is A minus lambda I x is equal to 0, and this has to be a non-trivial solution. This has to be a non-trivial solution. If it's a trivial solution, it is actually x0 straight away. And again, we said that a zero vector cannot be an eigenvector, only in some special cases, which we'll see shortly in a few minutes. So if and only if this equation has a free variable, right? So if this equation has a free variable, then there is a non-trivial solution, of course. Otherwise, with this matrix, you cannot have if you don't have a non-trivial solution, it means the vector x is 0 0. So this non-trivial solution is only possible if the elements on the diagonal, right, are non-zero, right? So if the elements of the diagonal become 0, right, so in this case, for example, if A33 becomes 0, okay, right, so in this scenario A33 minus lambda equal to 0, then A33 is equal to lambda, and this entry will become 0, right? So it means x3 in this case x3 will be 0. This x3 is 0, it means x2 is 0, and again being x3 0 and x2 0, it means x1 will be 0. So it means we have 0 0 0 as the eigenvector, which is not what we require, right? And again, say if this is 0, right, if this becomes 0, okay, so it means I don't have this equation to work with, only have I have 8 2 3 x3 equal to 0. It means x3 equal to 0. So it means if x3 is 0, this is 0, right? So if this is 0, this is 0, right? And again, so on and so forth, right? So it means what we have, it means that lambda could be any of the possible values of a11, a12 and a13, because there are only 3 possible values. So it means lambda could be equals to one of the possible values, entries in a11, a12 and a13. And similar is the case for the lower triangular matrix. So that we just have proved the theorem that the eigenvalues of a triangular matrix are the entries on its main diagonal. So if this is a matrix, A is equals to 3 0 0 6 0 0 minus 8 6 and 2. So it means the eigenvalue of this matrix is lambda 1 is equals to 3, lambda 2 is equals to 0 and lambda 3 is equals to 2. Similarly, if I say this is the matrix B, which is 4 0 0 minus 2 1 0 5 3 and 4, the eigenvalue of this matrix is lambda 1 is equals to 4 and lambda 2 is equals to 1. Because lambda 3 repeats itself, so lambda 1 is equals to lambda 3 is equals to 4. There are only 2 eigen values. Okay. Now the thing here is, we can see here that this is kind of a trivial solution. Lambda 2 is equal to 0 is a trivial solution. It means what we're saying here that ax is equals to 0 times x, right, and which has a non-trivial solution only in a scenario if A is not invertible, right? It means the rows or the columns of A or the rows or columns of A are linearly dependent. Okay, this condition can only apply a scenario when these are linearly independent or so linearly dependent, or they are actually non-invertible, right? So this equation only has a solution, right, as a non-trivial solution if A is not invertible. It means its rows and columns are linearly dependent. So the 0 is an eigenvalue of A if and only if, a double F, if and only if A is not invertible. If it is invertible, right, then 0 cannot be its eigenvalue, right? So continuing on with that thing here, so we can say if v1 up to v say f are eigenvectors corresponding to lambda 1 lambda r of an n cross n matrix A, then the set v1 up to vr is linearly independent. What it's saying here is that independent eigenvalues will produce independent eigenvectors. Independent eigenvalues will produce independent eigenvectors. I mean, you can prove this thing by contradiction, right? But we are not going to prove that. But we remember that if v1 and v are the eigenvectors corresponding to distinct value of lambdas, or in this case eigenvalues, then they are effectively linearly independent. These vectors are. So if you look at the utility of eigenvectors, we can think of from the point of view of the difference equation, that we know that x of k is nothing but a times x of k plus 1. And again, if you keep basically what we need to find a solution that for that scenario, right? So you can easily simply say that we need to find a solution for which ax is equals to lambda times x, right? So in this case, if I start from x naught, I can say that x of k is nothing but lambda times k into x naught, right? Simple like that, right? Starting from 0 position, right? You can keep multiplying, taking the power of the eigenvalues to find out x of k, because from the very fact here that a of x is equals to x, right? So a of x of k is nothing but equals to x of k, so, and you can keep building that, and what you will have here is you can show that ax of k is equals to a times lambda of k times x naught. It means lambda of k, you say, is a times x naught, because ax is equal to lambda x, so x naught is lambda times k lambda times x naught equal to lambda times k plus 1. From that analogy, you will have this as x of k plus 1. Okay, now we can do some examples and use those concepts that we have learned to solve those examples. So the first thing that we can do is 5 an eigenvalue of a, right? It's 5 an eigenvalue of a. So what you should do, it means a minus 5 times I times actually x should have a non-trivial solution, and it means we can find that that comes out to be if a is given as 6 minus 3 1 3 0 5 2 2 6, then a minus 5i will become as 1 3 2 minus 3 minus 5 2 1 5 1, and of course I can do the reduction here, multiply with 3, subtract here, multiply with 2, subtract with this one, and when I do that, that comes out to be, and augmented of course with zeros, so 1 0 0 comes out minus 3 4 8 1 2 minus 1. If you augment with zeros, that becomes 0 0 zeros, and if you do further reduction, it comes out to be 1 0 0 minus 3 4 0 1 2 and minus 5, and which is 0 0 0. Now you can think at you can see here, since it has no free variables, it means it doesn't have any non-trivial solution. Because it doesn't have a non-trivial solution, then it means it's an invertible matrix. It's an invertible matrix. It means all these rows or columns are linearly independent. It means that 5 is not an eigenvalue of a, right? Similarly, we can do another example. You can say that if a is an n by n matrix and lambda is eigenvalue of a, now we can show that 2 lambda is an eigenvalue of 2. So it is quite simple to prove that. It means what you can say that in a sense here that because lambda is an eigenvalue of a, so any non-zero vector for which that can exist is nothing but ax times equals to lambda x, and if I multiply with 2 on both sides becomes 2a times x is equal to 2 lambda times x. So now you can think of 2a as a new matrix B, and you can think of B as 2 lambda times x. So since B is equal to 2a, this eigenvalue corresponds to 2a, and that's why this statement is actually true. Hopefully you have understood this lecture, the concept of eigenvalues and eigenvectors. If you have any questions, please let me know through WhatsApp, Canvas portal, or comments on the YouTube video. Thank you. Allah Hafiz.